We'll continue the example from the last set of slides and look at how to report the chi-square statistic. We have a nice 2x2 table, a contingency table of counts, comparing people who report being a vegetarian or not, and those same people reporting whether they've ever had an episode of binge eating or not. Here's the table. In Stata, it's very simple to do. You say tabulate, which is a verb, and I think hopefully by now in Stata you've learned you can abbreviate a lot of stuff, so you can just say tab. Then say the name of your two variables, and then that comma is an option, and the option I want is chi-square. Stata will spit out this chi-square, which was 4.58. It's the same number we calculated by hand in the previous presentation, and the p-value, which we saw, is 0.032. If you like pointing and clicking your way through, you can see here this is a two-way frequency table from summary tables and tests. Here's how those data were reported in the actual literature. We see binge eating ever. We see the p-value is 0.05 and the chi-square is that 4.6. And remember, we don't just say, hey, there's a significant relationship, p is blah, blah, blah. We include two really important elements whenever we can. Remember, magnitude and directionality. And so these researchers report that 46, 67, those are the counts, and then you see the percents. And how they reported in the thing, higher percentage of vegetarians reported disordered eating behaviors. That kind of implies a little causality, right? That it's the vegetarian that's driving the binge eating. But be careful. It might not be. Now, I want to show you a little bit about this percent in here. They report a percent, 44%. This is a common mistake that you will see all over the place. Everybody will make this mistake. You can make any mistake that you want one time and then learn from it and stop making that mistake. And this is a mistake I would much rather you make in this class and we correct it than you actually make out in the real world waving your Tufts MPH. The mistake is this. You can get a row or a column percentage to summarize up the results of your research. I want you to look at this cell right here. This cell right here is the cell of yes, vegetarian, yes, having a binge eating episode. There are 46 people in there. But we see that there are 2%. There's a row percent and there's a column percent. And you look at those two numbers and you have to think carefully. One of those numbers is the percent of vegetarians who have ever had a binge eating episode. And one of those numbers is the percent of people who've ever had a binge eating episode who are vegetarian. And I know that sounds like gibberish and they sound like the same thing, but they're different. The row percent and the column percent is different. And I'll give you an example that I hope will cement this into your head. Ask yourself this question. What percent of mothers are women? Okay. 100%. Or what percent of women are mothers? Well, not 100%. Thank God. Not everybody wants to be a mother. So the percent of binge eaters who are vegetarian is different than the percent of vegetarians who are binge eaters. And if you mix these things up, you can say some very dangerous statements. Let me show you how to read this correctly. What you want to do is, I recommend, take the table and do the numbers by hand so that you can make sure that you always do it right. Here's our table. We have veg, no, and veg, yes. And for binge, we have binge, no, and binge, yes. And so when we look at the numbers from this table, I didn't actually memorize these. I have them carved into the table in front of me. 210, 104. All right. So I recommend that when you write this sentence, you calculate it by hand and then go back and double check the Stata output. So what percent of vegetarians ever had a binge eating episode? All right, well, I have to look. How many vegetarians do I have? Here's my vegetarian, yes, 104. So I have 104 vegetarians. Of that 104, when I look in this row, how many have had binge eating? 46. So 46 divided by 100. Athena, are you there? What's 46 divided by 104?
It's 44%.
You just do that off the top of your head?
I sure did.
Wow. All right. 40, that's impressive. 44%. Now, the other thing, which I told you is going to sound the same, but it's not, is what percentage of people with a binge eating episode are vegetarians? Okay, so now we need to look in this column, and we have 113 people who've ever had a binge eating episode. And how many of them are, well, that's that 46, right? So now we see 46 divided by 113, and that should be, what is that? Just tell me, I was going to guess.
40%.
All right, 40%. So this is really important. Do not mess this up, and make sure that the numbers you're reporting always make sense. Make sure that they always make sense. Now, the tables can be bigger than 2 by 2, and we'll give you some practice on this in some homework. Is there a relationship between whether a house is on a corner, yes or no, and what color that house is? 2 categorical variables. How do I find a relationship? I calculate the chi-square. And here you look at the p-value and say, there is no evidence that there's a relationship between these 2 variables. Here's another example. This is from the literature. This is an older example, but I like it. I like it. So we have gender and ethnic differences in foods in students' lunches. Okay? Now, there are a lot of data on this table, and you'll find that when you run your analyses, you can cram in a bunch of different tests into one table. So if you look here, there's a bunch of chi-squares here. Each one of these is a statistical test. Each one of these is a table. Each one of those has expected and observed. You might have 50 pages of data output to make a table like this. Those chi-square statistics get turned into p-values. And so this asks the question here. For example, let's look at sand meat, which I assume is sandwich meat. Is there a relationship between whether you have meat on your sandwich and whether you're a boy or a girl? Now, I really hope the answer to that is no. So let's take a look. We see that 87% of boys use sand meat, 88% of girls use sand meat. That's a very low chi-square statistic, and therefore the p-value is high. It's not statistically significant. It's a nice 2 by 2 table. What if you wanted to see if there were ethnic differences in the use of different foods in common school lunches? So, do you use cheese? Yes or no? What type of variable? Binary. And then this conceptualization of this variable, which is Asian Pacific Islander, Black African American, Latino Hispanic, white, or multi-ethnic. 5 different categories. So we have a 5 category variable and a 2 category variable. Is there a relationship? We run chi-square. And what we see is that for cheese, look at the p-value for cheese, 0.043. There is a statistically significant difference in cheese use among kids of these different groups. That's the homogeneity of proportions. And if you take a look, you can take a look, in total, 72% of these kids have cheese. But that is lower in Asian Pacific Islander, higher in Blacks and Latino Hispanics, lower in whites, and higher in multi-ethnic. Now, the null hypothesis here is homogeneity of proportion. Are all the proportions equal? This p-value rejects that and says they're not all equal. Now, we don't know exactly where it is. We don't know what groups of kids are different than other groups of kids. All we know is there's a relationship. There's something that's going on. There's a twist to the chi-square test, and they come from this guy, Fisher. And Fisher had this really interesting idea. He said, I'll simplify it, but he said, if the whole goal of this is to say, how weird are my data? How weird is this table of 143 and 67 and 58? How weird is that table relative to what I would get if the null hypothesis were true? Fisher sat and puffed his pipe and said, you know what I could do? I bet I could just make all possible tables. I'll just make all the tables that could happen if the null is true. And then I'll take those tables and I'll line them up in a row from the least weird to the most weird. And then I'll take my table and say, hey, look, shit, there's my table. What percentage of the tables are higher than that? What percentage are lower than that? That tells me the probability of getting results like mine or more extreme if the null hypothesis were true. This is a great way to calculate p-values because it's exactly what it is. That's why it's called Fisher's exact test. I'll give you a general rule. Whenever you have an exact test, use it. The problem is it's hard to do computationally. You have to make all possible tables, and only recently was this available in statistical software program for big tables. So Fisher's exact test, and this is what we just said. Construct all the possible, now don't do this, the computer does it for you. Make all possible tables. See how many more tables are weirder than yours. What percent of tables are weirder than mine? That's my p-value. And here's my recommendation to you. When you have Fisher's exact test, here, I'll just say this. Let's say it like this. Who knows what will happen since I'm filming this, computing power-wise. When you have Fisher's exact test, use it. Use it. Now, like any test, there are some assumptions and there are some limitations. For chi-square, you have to be careful. When you have small expected cell counts, and the general rule is that if 80% of your expected cell counts are less than 5, the test kind of breaks down a little bit. This is not a strict rule. This is just a guideline. But be careful when you have expected cell counts that are small. Not observed, but expected. And then we talked about this a few times. The chi-square usually comes from cross-sectional survey data, some sort of tabulation of what's going on right now, this point in time. And we have to be very careful about causality. All we can say is these two things are related. The chance of being in this cell is related to the chance of being in this cell.